Good evening, everyone. We are here for the sixth day of our faculty development program conducted by Department of Mathematics in association with Kerala Mathematical Association at PRDS College, Changanasheri. I welcome all of you for the sixth day of our session. Now I welcome Ms. Vani Srikumar, Assistant Professor, Department of Statistics, for the welcome speech.
Good evening, everyone. It gives me great pleasure to extend a warm welcome to all of you present here for the sixth day International FDP on the topic Real Applied and Computational Mathematics, organized by Department of Mathematics in association with the Kerala Mathematical Association. I would like to introduce our today's resource person, Dr. Rakesh Kumar, Senior Assistant Professor, School of Mathematics, Sri Mada Vaishno Devi University, Katra, Jammu and Kashmir. It's my privilege and honor to welcome you, sir. Welcome, sir.
Thank you, ma'am.
And also, I welcome all the participants to this informative section. Over to you, sir.
Okay, thank you, ma'am. So, first of all, I would like to thank the organizers of this International Faculty Development Program, especially Professor Jayanthi and her team for organizing this program successfully. My thanks are also to the Kerala Mathematical Association for cooperating with this program. Okay, so today I am here to present my topic on queuing theory, and the topic is role of queuing theory in cloud computing. So let me share my screen. Is it visible? Is my screen visible? No, no. Okay, let me present. Is it visible now? No. Okay. I think now it will be okay. I think now it is visible. Okay. Yeah. So my topic is role of queuing theory in cloud computing. So the objective of this talk is to provide a link between queuing theory and cloud computing. We will try to see how this queuing theory can be applicable in cloud computing framework. How this theory can be useful to the cloud computing people for performance analysis of such system and the designing of such systems. So before first of all, I would like to go through some basic ideas of queuing theory, and then I'll move to cloud computing, and then we will try to establish a relationship between cloud computing and queuing theory, and then I'll discuss some research works which use queuing theory in cloud computing. So first of all, whenever we talk about queues, it means waiting lines of customers seeking some sort of service at service stations. So why we need to do mathematical analysis of such kind of systems, queuing systems? Why there is a need to study queuing systems? Because very useful time or a precious time is wasted in waiting. Okay, and sometimes the waits become very harmful whenever we talk about patients waiting for heart transplant, or some kidney failure patients going to hospital and they have to wait. In that case, no there could be casualties. Okay, so this queuing always kills our precious time and money. So that's why there is a need. And queues we can see everywhere. Okay, you all in your daily life you see the queues. used at bus stations, railway stations, airports, post offices, banks, and so on and so forth. Okay. So how to study it quantitatively, how to study the queues quantitatively, how to come out with the wise decisions based on numerical analysis or quantitative analysis. So that work is possible only with the help of queuing theory. So queuing theory is nothing but it deals with the mathematical description or analysis of queuing systems, right? So what is, before starting, the first thing here is queuing system. We need to know which queuing system we have to study, or what is the underlying queuing system. So a general form of queuing system is represented here in this diagram. You can see the arrival process, customers arriving from the population for service at some service system. Okay, if the service is not immediate, they will have to wait in queue. Okay, and then after getting service, they move out of the system. Okay, so departed customers, right? So service system consists of one or more than one customers. So this is the typical diagram of a queuing system. So first of all, we need to understand what a queuing system is. The second thing is trade-off between cost and level of service. So while designing any queuing systems, okay, we have to be very careful about the costs involved. So this side y-axis we have cost of operating service facility, okay, and then on the x-axis here, horizontal axis, we have service level. So the customers are always interested in higher service levels, but at the same time, the service provider will have to see the underlying costs. Okay, so there are mainly two kind of costs in queuing theory. One are cost of providing service, and second is cost of waiting time or cost of holding customers. So as we increase the level of service, we can see here the cost of providing service definitely increases, because we will have to invest in our system. We will have to employ more servers, okay, or some other facilities we have to arrange. Okay, so whenever this level of service increases, definitely the wait time of customers will decrease and the waiting cost of customers will be down. Okay, so we will have to okay, then what is the total cost? Total cost is the sum of service cost and the waiting cost. Okay, so we will have to satisfy ourselves somewhere where there is a optimal level of service, that is the total cost is a minimum. Okay, but okay, this is the optimum level of service. If we go beyond this, we can see that the total cost will increase. Okay, so that's why one need to have such kind of trade-off between level of service and costs. Next is how to characterize a queuing system. Which things we will have to take into consideration. One is arrival process, then or arrival pattern. The second is service process, service pattern, number of servers, capacity of the system, and queue disciplines. So this arrival process is very important. We need to understand how the customers are arriving into the system. Okay, in real life, we can see that we cannot predict the arrival of any customer. So that's why the arrivals are random in nature. So in order to model the arrival process, we will have to take into consideration the probability distribution of inter-arrival times, right? Similarly, the service process. The service process is a process, or service pattern is a pattern in which the customers are provided with service. So there may be one server or more than one servers, and similarly, no, each customer may take different time of different may require different amount of time for service. So that's why the service times are also random in most of the times, and then we will have to take into consideration the underlying probability distribution for service times. So both the processes are random in nature. The number of servers, these may be one or more than one. Whenever there is one server, we call single server queuing systems. Whenever there are two or more servers, we call those as multi-server queuing systems. Then the capacity of the system. Capacity of the system means how many customers a system can accommodate. Is there a limit, or there is no limit? That's the infinite capacity queuing systems. So there are finite capacity as well as infinite capacity queuing systems. Okay, Most of the times we find finite capacity queuing systems. Queuing discipline, though how the customers are taken for service. So commonly used queue discipline is first come first serve, last come first serve, service in random order, and then certain priority queuing disciplines. For more information, one can read the fundamentals of queuing theory by Gross and Harris for more details. Okay, or the stochastic processes by J. These two books are very fundamental to understand the stochastic processes as well as the queuing systems, queuing models. Okay, next is Kennalls notation of a queuing system. Okay, so this Kennalls notation consists of A slash B. We simply read it like A, B, C, D, E. A refers to inter-arrival time distribution. B refers to service time distribution. C, number of servers. D, capacity of the system. E, queue discipline. Okay, for example, let us consider this MM1. So first letter here A is replaced by M, second letter B is replaced by M, then 1, and then other letters are missing, means by default they are like D is infinity, infinite capacity, and E for queue discipline, it is first come first serve. So whenever these last two letters are omitted, it simply means the capacity of system is infinite and queue discipline is first come first served. So here M for Markovian means their interval times are Markovian in nature, service times are Markovian in nature. Exponential distribution possess this property of this Markov property, that is forgetfulness property. Okay, this property says that the future occurrences, the future developments are dependent only on the present state and not on the past. Okay, so the second one is MM1N. Here the capacity of the system is finite. So we have the whole idea of a queuing system simply by its nomenclature. Okay, MG1. So G here, a different symbol is coming now. So this is for general service time distribution. Here the service time distribution is not properly defined. No pattern is here. So we assume that the service times are this continuous and distributed generally. No proper this framework of any probability distribution. Okay, then is MMCN. So C here, no, C number of servers, finite number of C servers, capacity of the system is finite. And other next letter is absent, means queue discipline is discipline is first come, first served. So this is about the Kennalls notation of a queuing system. Next is, okay, why we study these queuing systems? What is the idea of defining these symbols and all that? Okay, what we do, we are interested in knowing, what is the average if a customer goes and join the system. Okay, what will be the we are interested in predicting what will be the average waiting time of a customer in the system. What will be the average number of customers in the system at any time? These are the main questions that we need to answer with the help of queuing theory, and that's why we develop some mathematical models to find out the probabilities first. Okay, probabilities of number of customers at a particular time. Okay, and then after that we are interested in finding these measures of performance. Average number of customers in the system denoted by LS. Okay, this is common symbol in queuing theory for this. Average number of customers in the queue, LQ, average waiting time of a customer in the system, WS, average waiting time of a customer in the queue, WQ, and then average server utilization, which is the ratio of mean arrival rate and mean service rate. Okay, then there is a Little's law. Queuing theory people know this very well. This law relates this average number of customers in the system with the average waiting time of a customer in the system, uh, provided we know this mean arrival rate lambda. So this is the relation. Okay, if we know any one measure, we can find out others with the help of this Little's law. Okay, coming to the very first, very preliminary queuing model. Okay, there are many other queuing models available in queuing theory, but we must have some idea about the basic queuing model before moving to its relationship the relation between the the application of queuing theory in cloud computing. The here it says that arrival to the queuing system occur one by one according to a Poisson process with mean rate lambda. So if some events occur according to Poisson process, then inter-occurrence times, that is here inter-arrival times, are exponentially distributed, and exponential distribution possesses Markov property. So that's why this M here for arrival process. Similarly, single server, there is single server, and the service times are exponentially distributed with parameter mu. Okay, capacity of the system is infinite, and queue discipline is first come first serve. So these are the assumptions of the queuing model, and these are very clear even from the Kennalls notation of this queuing model MM1. Okay, then coming to the next part, very very important, how to have a mathematical model under these assumptions. So first of all, we define the probability. Okay, so let P and T be the probability that at time T there are n customers in the system, and n may be from 0, no customer, 1 customer, and so on. Okay, so based on the memoryless property, that is the Poisson process, okay, we get for delta t tends to 0, okay, p0 t plus delta t is equal to all these things 1 minus lambda delta t, okay, plus o delta t is the probability of no arrival, mu delta t is the probability of one departure, okay, and o delta is a function which approximates all the higher order powers of delta t. So what do they say that no, we are interested in delta t, but what happens during delta t time? So we are interested in no, the system is empty at time t plus delta t. Okay, so if there are zero customer in the system, system is empty at time t and no arrival occurs, then there will be zero in the system at t plus delta t time. Then if there is one customer in the system and during delta t one departure happens with this probability mu delta t, okay, then there will be 0, okay, and then this is o delta t as defined earlier. So next step is just simplifying the expression and dividing throughout by delta t and taking delta t tends to 0. So from this expression we get p0 dash t, that is dt of p0 t minus lambda p0 t plus mu p1 t, where limit tends to delta t tends to 0, o delta t upon delta t tends to 0. Okay, so similarly we can have another equation for n number of customers which are different from 0 and running from 1 to 3 and so on. We can have a second equation for n number of customers, ddt of p and t is equal to lambda pn minus 1t minus lambda plus mu p and t. Okay, here it means no arrival, no departure, n. Okay, n minus 1 in the system at time t, during time delta t, one arrival occurs with rate lambda, and then there will be n. Okay, and similarly n plus 1 in the system, one departure, and only n after time at time t plus delta t. So using the same arguments we can develop this equation. So now we have two differential difference equations here. I can solve these either in steady state or in transient or time dependent state. Okay, so whenever we talk about time independent or steady state, means time is very very large, the operating characteristics become independent of time. Okay, the probabilities become stationary. Okay, at that time point this p0t becomes independent of time, so derivative of this becomes 0 here, and similarly 0 here. On the right hand side we remove from here because probabilities are independent of time, so we get these difference equations only, and then we can solve these in iteratively, okay, to get the value of pn, right? So after we obtain Pn, we can find out the expectations, that is summation nPn, which will give us the average number of customers in the system. And then once we obtain that, we can find out all other performance measures using Little's law. So this is very simple single server infinite capacity queuing system. We can have finite capacity single server system with Markovian arrival and services. Okay, Then we can have many other systems. We can develop the differential difference equations this way, and then we can solve them using various methods to obtain the probabilities of system size, that is the probabilities of number of customers in the system. Okay, the next thing we need to understand is not a single queue but a combination of queues. Okay, a large number of queues are connected to one another. Queues may be connected in series. Okay, the one queue's output is the input to the other queue, and similarly the second queue's output is the input to the third queue, and so on. So we call these kind of systems as serial queuing networks or tandem queuing systems. There may be queues which are connected heterogeneously. Okay, so we can have heterogeneous network, a very simple and very first or standard queuing network, open queuing network, that is Jackson queuing network given by Jackson. So we need to understand a Jackson network is a system of M service facilities, I from 1 to M, which has an infinite queue, means there is no restriction on number of customers arriving from outside the system according to a parser input process. This is the specification of Jackson network, that here the customers arrive from outside according to parser process with parameter this SI servers with exponential service time distribution with parameter mu I, and a customer leaving facility I is routed to next facility, that is J, or next queue. Okay, J, the J from 1 to M with probability Pij, or it departs the system with the complementary probability 1 minus summation J from the means all other probabilities. Yes. So sum of all this routing probabilities 1 minus this, that is the probability of moving out of the system. And any such network has a following key property, that is under steady state conditions, this is the balance equation. So this arrival rate lambda j can be computed by using aj plus I from 1 to m lambda I Pij. So these are balance equations, and once we are able to formulate this, we can find out all other rates, and then we can find out the underlying probabilities, joint probability of having different number of customers in the system. This is a diagrammatical representation of Jackson queuing network. Okay, here therefore from various streams the customers are coming and joining with this rate lambda I at this service facility mu I, and from here, okay, this customer can go to all other queues with probabilities ri1, ri2, rim, or they may leave the system with this probability out of the network. Even the customers may go back to the same service facility as a feedback customer with probability RII. So this is the representation of a Jackson network, and very important theorem is Jackson theorem, which says that the steady state probabilities, the joint steady state probability of the network, that is if it is denoted by pi, then the joint steady state probability of having k1 number of customers at node 1 q1, k2 number of customers at q2, and kn number of customers at kn. This is simply given by the marginal probabilities, okay, of different queues, that is k1 number of customers probability, steady state probability of having k1 number of customers at q1, and steady state probability of having k2 number of customers at q2, and product up to so on the probability of having a kn number of customers at node kn. So the joint probability is simply the product of marginal probabilities. These can be very easily found simply by solving the each queue, okay, as a independent queuing system. So this is for mm1 queue. Okay, if we consider each queue as mm1 queue, we can have the same formula when we have multi-server queues also. Okay, So now coming to the next part. Okay, so till now, what we have done, we simply came to know what is queuing theory, why we should develop queuing models, and what are the cost and level of service trade-offs. And after developing mathematical models, we solve them and we obtain various measures of performance through which these measures of performance help us to design any kind of queuing system, even in the optimization of the existing queuing systems. So after knowing this, now we will try to get familiar with cloud computing systems. So first of all, what is the meaning of cloud? So cloud refers to servers that are accessed over the internet. Now we are not directly working with you know the supercomputers or any other supercomputing facilities or extra storage facility directly, but we are accessing those through servers, okay, that can be accessed via internet, okay, and the software and databases that run on those servers, right? Now cloud servers are located in data centers all over the world. So data centers consists of a number of computers, okay, over there, and then their combined capacities can be utilized through these cloud servers. By using cloud computing, users and companies don't have to manage physical servers themselves or run software applications on their own machines. Rather, they can access all that with the help of these clouds, okay, through internet. Now this is a typical diagram for any cloud. So here, suppose this is my laptop and I am accessing everything over my laptop with the help of internet, and this is data center somewhere consisting of various servers, okay, and then applications and databases. Now, what is cloud computing? It is a technology of distributed data processing in which some scalable information source resources and capacities are provided as service to multiple external customers through internet technology. Now, what is distributed system? It is the one in which computers located at different places communicate only through messages. Okay, so distributed system. In fact, internet is also a distributed system. Okay, so then the resources are shared dynamically and services are provided to customers on demand. Thus, the users have to pay only for the duration they utilize the cloud resources. Okay, so it is on demand availability of computer system resources, especially data storage, cloud storage, and computing power without direct active management by the user. Over the recent years, research shows that there is higher growth in cloud computing among companies with higher revenues. This is because of availability service at lower cost and economically scalable. So one can have economically, you know, available services through cloud computing or through clouds. Okay. Now there are various service models of cloud computing. One is software as a service, SaaS. Instead of user installing an application on their device, SaaS applications are hosted on cloud servers and users access them over the internet. For example, you know, we are using this Google Meet, Google Apps, GoToMeeting, Cisco Webex systems, Dropbox, etc. These come under SaaS, okay, of this cloud computing. So the SaaS is just like renting a house. Landlord maintains the house, but the tenant mostly gets to use it as if they owned it. Okay. The next is platform as a service. Second service model is platform as a service. In this model, companies don't pay for hosted applications. Instead, they pay for the things they need to build their own applications. Okay, so here uh, they need whatever they need. Okay, they develop their own applications, but whatever they need, they only pay for that. Okay, to the cloud service providers. So PaaS vendors offer everything necessary for building an application, including development tools, infrastructure, operating systems over the internet. PaaS can be compared to renting all the tools and equipment necessary to build a house instead of renting the house itself. Okay, so these examples are Windows Azure and Google App Engine. So these are the examples of. So with the help of these, one can develop their own applications, right? So next is infrastructure as a service. In this model, companies rent the servers and storage they need from cloud provider. Then they then use that cloud infrastructure to build their own applications. So you can see, for example, this DigitalOcean, Google Compute Engine, and OpenStack. Okay, so earlier these were only there were only three models of service models of cloud computing. One more has come now, that is function as a service. So function as a service, also known as serviceless computing, it breaks cloud applications down into even smaller components that only run when they are needed. So imagine if it were possible to rent a house one little bit of time. For example, tenant only pays for dining room at or during dinner time, for bedroom while they are sleeping, and living room while they are watching the TV, and when they are using and they are not paying when they are not using the rooms. They don't have to pay, okay, the rent on them. So this serviceless applications still run on the servers and do all these models of uh, cloud computing. Now, coming to next thing in cloud computing is service level agreement. This is very important thing. It's a part of service contract where a service is formally defined. So particular aspects of service are scope, quality, responsibilities are agreed between the service provider and service user. A common feature of this is response time at service stations. Okay, so response time is what? It is defined as the time for a request to be serviced. In other words, the sum of waiting and servicing times in a cloud. Okay, so whatever agreement has been made between the two, that okay, this will be the response time, they will have to abide by that. Okay, so this comes under service level agreement. Now coming to the quality of service characteristics or quality of service in cloud computing, this is most important, especially when we apply the queuing theory. So the application requirements can be characterized by quality of service requirements such as availability, security, reliability, as well as many other parameters. But performance indicators are such as response time, task blocking probability, probability of immediate service, and mean number of tasks in the system. So here probability comes under picture. So if we develop certain queuing models, we can study these descriptive measures like mean number of tasks in the system. So here tasks are just like customers, okay, ls, and then probability of immediate service, mean what is the probability that there is no customer in the system, and then task blocking probability, that is probability when the system is full, and okay, response times. Okay, so like this. So what is the total time taken for servicing a customer or a task. So these are the quality of service characteristics. SLA is a legal binding contract, as told earlier, which states QS guarantees that an execution environment agrees to provide its hosted application. So this is simply a promise, okay, that service provider gives to the customers, okay, who needs the services. The ability to deliver guaranteed quality of service is crucial for commercial success of cloud service providers. Next is virtual machine. So virtual machines are computers that run inside other computers using process known as virtualization. So in cloud computing, the services are provided with the help of this kind of virtual machines even. The virtual machine is a software based computer that exists within another computer's operating system, often used for purposes of testing, backing of data, or running SaaS applications. Classifier now. Classifier is placed to check the requests or jobs. More specifically, to serve jobs, first they send their bots through networks and the classifier captures their requests. A bot is a software application that is programmed to do certain tasks. Bots are automated, which means that they run according to their instructions without a human user needing to start them up. The classifier can be placed in SAS, PAS, and as IAS environment or as an independent node. Now comes the resource allocation. Okay, what are the resources available with the a cloud service provider? Okay, resources in terms of computers, in terms of the services. Okay, so what are the resources? In cloud computing, resource allocation is a process of assigning available resources to the needed cloud applications over the internet. Resource allocation strategy is all about integrating cloud provider activities for utilizing and allocating scarce resources within the limit of cloud environment so as to meet the needs of cloud application. It requires the type and amount of resources needed by each application in order to complete a user job. Now, connection with queuing theory. So, before this, we simply can understand that queuing theory is
Dear participants, some connection problems occurred for the resource person. Please be online. He will join in a minute.
Am I audible now?
Yes, sir, it's audible.
Okay, okay. So I'm again presenting. Yeah. So sorry for this inconvenience due to net connectivity, I think. Okay. So again, yes, I was here. Okay. So these applications usually use standard web protocols to assess the system and authentication protocol, which allows access to authorized users. The backend functions include management of job queue, the servers and their virtual machines, and storage servers with the database system. So here in the backend, there are queuing systems. Okay, database inconsistencies, if any, those are avoided simply by considering only one storage. Then the cloud is considered as a single access point for computing needs of the customers being served through web browser supported by web server. Service center is a collection of service resources used by service provider to host service applications for customers. Now the service request from user is transmitted to web server running a service application associated with an SLA. This process is performed at the front end. Thus, the customer, who may represent multiple users, generates service requests at the given rate for processing at service center. Okay, so here the service requests form queue, okay, hosted by service provided through the cloud according to negotiated quality of service requirements at given price. So here I am giving a diagram of cloud computing infrastructure, which is discussed by Villaplana et al. In 2014. And this is the cloud computing infrastructure is considered as a queuing network. Okay, so this queuing, they have considered a queuing network model. So here you can see that there is an entering server. The outside requests are coming through the entering server here, and then they are entering server works just like a load balancer. So load balancer allocates the jobs to various processing systems, PS1, PS2, PSM. Okay, if there are these systems, processing servers. Okay, after that they are routed to this either to the database server for database kind of services or to the output server with different probabilities as shown here. And then after output server next sends the processed works jobs to the client server and then to the end server, end consumer. Okay, so this is how the different service processes can be modeled as a queuing network model with the help of queuing theory. Okay, this network has single entry point, entering server. The server acts as load balancer, which forwards the user request to one of the processing servers, as told by me just now. The load balancer is represented by MM1 queue. So we can assume, we can consider the load balancer simply as this Markovian single server queue. Okay, so then it can be handled. Its purpose is simply to determine PSI node to deliver the service. In doing so, it uses an algorithm that distributes the request depending on the average workload in each PSI processing server nodes. Okay, Next is a processing server is a node representing the physical computational resources of the cloud architecture where the services are computed. The selected PSI node performs all the services required by the user request. This PSI is identical and is modeled as MMM or MMC, M server or C server queuing system. Okay, each having the same service rate, that is identical. So each PSI node accesses DS with probability delta. So DS represents database server and serves to the model the access to files, directories, and databases or any kind of input-output access to secondary memory during the service in cloud architecture. An important consideration to be taken into account, because input-output interference between the virtual machines is an important issue, so it's avoided by considering only one database server. DS is again modeled as MM1Q, okay, with the respective exponential and arrival and service rates. And then coming to output server, OS of the cloud architecture. OS is node forming the cloud architecture that transmits the response data over the internet back to the client that made the original request. So CS is the client server. Client server sends the requests in an exponential distribution with parameter lambda to entering server. Okay, so it also receives responses from the cloud architecture. So now this client server receives files or pieces of files until request is fully satisfied. So both OS and CS are modeled MM1 and MM1Q. Okay, so this is how this queuing cloud computing system having different kind of servers at the back end can be modeled as a queuing network model. So once we are able to frame or model this as a queuing network model, we can use the Jackson network for its analysis, okay, or we can use any other networks, okay, which are required, which are available in queuing theory. Now coming to the second model given by Hu et al., dynamic performance optimization for cloud computing using MMM queuing system. Okay, MMM means multi-server Markovian queuing system. So in this paper, data center is modeled as service center, which can be used as MMM queuing system with multiple task arrivals and task request buffer of infinite capacity. Means there is no limit on the number of requests. Okay, infinite capacity and queue discipline is first come, first serve. So they have done the dynamic performance optimization. So they have considered this model and they have done the optimization of the same model to study the, this cloud computing system or data center, cloud computing data center. Okay, so this is the diagram of the underlying queuing system. So different requests come via rates lambda 1, lambda 2, lambda this, and the total arrival rate, which is lambda. If these come under Poisson process, then the sum of Poisson distributed variables again is a follow Poisson process of Poisson distribution. So again, this is Poisson distributed. So lambda is sum of all these arrival rates. So here it is a queue, and then the scheduler sends the tasks to different servers, M servers here. Okay, and whenever all the servers are busy, the remaining requests will have to stay in the queue. Okay, and we can use the mathematics of MMC queuing system here, MM1 queuing system here to find out the probabilities of number of tasks in the queue or in the system. Now we can answer various quality characteristics like probability of immediate service, probability of this rejection, and waiting times. We can study the waiting times of the jobs, and this or the buffer size, etc., etc. All these kind of things can be answered with the help of this multi-server queuing system. Another model that I want to discuss here, developed by this K. Shanti and Sravanan, performance analysis of cloud computing bulk service using queuing models. So now once we are apt with this application of queuing models to the cloud computing systems, now there are a number of queuing models available. There are batch or bulk service queuing models available. So they have used this batch service or bulk service queuing model, single arrivals occurring singly, one by one, in according to this voice of process. Okay, then the exponential service, but service occurs with batches, in batches. Okay, so batches of variable size or batches of fixed size. So this my denotes y is the batch size. So this denotes the service in batches and single server. Okay, so they have used this. So the system here means cloud system, computing system. So this is the underlying assumptions here. The server is free, different class of clients. User enter the system with probability 5 for getting service in batches of size k, and leave the system after service completion. Otherwise, they can leave the system before getting service also with probability 1 minus 5. Okay, so right, so this kind of leaving the system before getting service, this process is known as renaging. Okay, so these are the different lambda is arrival rates, right? Now this is the diagrammatical representation of the system they have considered. So batch service model in cloud computing architecture, so clients, users, okay, they send requests. Okay, the requests are handled by the server, bulk server, so they are handled in batches, right? So okay, sometimes the requests are dropped even with probability 1 minus 5, and with 5 these are with probability 5 this goes to the service, right? So this is the diagrammatical representation. Okay, next coming to okay, nowadays we have also started working on modeling cloud computing systems using queuing theory. So this is our paper. uh, okay, performance evaluations of a cloud computing physical machine with task renaging and task array summation. So task renaging simply means that no tasks are dropped before taking them to service. Okay, or tasks get timeout if they are not processed within certain time frame. Okay, and the drop tasks are resubmitted, or these are considered as feedback customers for further transmission or further processing. Okay, so this is the task renaging or task dropping. Renaging or drop tasks could be resubmitted provided they were not dropped due to security reasons. So in this paper, what we have done, we have presented simply MMCN queuing model. So this is Markovian input, Markovian output, C number of servers, finite capacity. So we have proposed this model for cloud computing physical machines, where the interval times and service times are exponentially distributed. N is the buffer size, capital N. C in virtual machines, number of servers running in parallel. Okay, so we have studied the effect of task renaging and task resubmissions on the queuing delay, probability of task rejection, and probability of immediate service. Okay, this is the diagrammatic representation of cloud computing model here. So the requests come over internet, and they are processed like this. So load balancer sends them to different physical machines here, and we can see that now the before processing the tasks are queued in queue. Okay, then they are assigned to by the load balancer or task scheduler. They are assigned to different virtual machines. Okay, and then the tasks can be rejected, or they may time out. Okay, if they are not served before the prescribed time limit. And then these are the assumptions. Simply, these are the assumptions of MMC and queuing model. So arrivals occur according to Poisson process with parameter lambda. The system has single queue and finitely many servers, virtual machines. The processing times at each virtual machine are exponentially distributed with parameter mu. The mean processing rate of the system is n into mu because there are n number of c number of processors. If the number of tasks are less than the number of processors, then the service rate is n mu, and if the number of tasks or jobs are more than the number of servers, then the service rate of the system becomes c into mu. The queue discipline is first come first served. Capacity of the system is finite. Renaging times, or the times at which tasks are dropped from the queue, are exponentially distributed with parameter psi. When a task renages or is dropped from queue, it can be resubmitted with the probability p, otherwise with probability q1 minus p, it is not resubmitted. So this is the underlying mathematical model for this system. Okay, so DDT PNT and DDT PNT here. So this is differential difference equations for n is equal to 0 and different values of n here. These are built on the same basis as I have shown earlier for MM1 queuing model by using birth death process arguments. Okay, so here this underlined here means with the probability q into mu, the tasks are tasks go without no tasks are served, and with probability mu p into mu, these rejoin. Okay, so this is feedback probability here, or the service rate now. And then here this underlined part is, if there are n in the system, so n minus c will be in the queue. So the number in the queue multiplied by the renaging parameter, this gives me the total renaging rate. So with this rate, customer renages, isn't it? So even I have done a lot of queuing models on this renaging and retention of renaging customers. So one can refer those basic models or other models for this kind of for understanding these kind of models. Okay, so we have done a lot of steady state analysis of the system as well as the transient state using Rangikuta method. Okay, and I'm showing you one two graphs, not all. Okay, so as we increase time, what happens to the average delay in queue or waiting times? Okay, so I have compared two models. There's multi-server queuing system with the renaging and multi-server queuing system with the renaging and feedback. So in case of this multi-server queuing system with the renaging and feedback, we have higher delay. Okay, because here more jobs join for a reservice. So that's why the queue size is more, and definitely the waiting time will be more. And the second one is what is the effect on probability of task blocking. So again with time, so as the time increases, this probability of task renazing blocking increases, and after some time it settle down, so it becomes steady. Okay, so again if we compare these two models, we find that in case of feedback queuing model, this probability of task blocking is more, because the queue gets full more often than this model without a renaging, isn't it? So the next one is arrival rate lambda. What is the
Hello, sir.
task blocking probability or task blocking can be minimized. So this is all about what I wanted to discuss. I think the participants might have got some idea that how we can use this queuing models or queuing theory in modeling cloud computing systems. So new researchers may get more exposure to this
Yeah. Hello. Hi, sir. So thank you so much, sir, for the wonderful session. Actually, it's informative so too. And we get a clear picture about, we get a brief picture about what is cloud computing and something like that. Thank you so much for this session. We will look after you into another session. Okay. Thank you so
Okay, thank you, ma'am.
thank you so much, sir.
Okay.
Thank you. We will look
Yeah,
after you into
thank
another
you.
session. Thank you.
Yeah, thank you, ma'am.
Dear participants, please fill the feedback form that is posted on the description box and also in the live chat box. It's also open now and it will close soon. Please don't fail to fill the same, because certificates is issued by using the same only. Tomorrow will be the last session for us, so please fill the feedback form without any fail. Thank you. We will meet tomorrow.